switch capacitor circuit, we are using MOSFET as a switch, and we use the capacitor. So this is a discrete time system. So in a continuous time circuit, the input signal and output signal is continuously available. So application of continuous time circuit is audio, video, and high speed analog system. So in a discrete time system, we may sense the input for some periodic instant and ignoring its value for other times. So the circuit will process each sample and producing a valid output at the end of each time period, and such circuit we can call as a discrete time circuit. So we are using a MOSFET as a switch. So discrete time circuit, that is a switch and capacitor. So we apply the input, we will say whenever the switch is turned on, the input is available, you can access the input, it is stored on the capacitor and you will get the output. So we are using a MOSFET as a switch. So we apply the clock signal here. Whenever clock is high, this transistor will turn on, it will apply, input is available for you, you can access that input. Whenever this clock signal is low, transistor is off, so switch is off, so you will not get the input for that range. So this is a switch capacitor circuit. Now see this, whenever this clock signal is high, so input is equal to output. So when this clock signal is high, the transistor is turned on, so switch is closed and output is equal to input. So see, this is the circuit for this. So whenever this clock signal is low, the transistor is off, so switch is off, so output having some constant value that is previously stored. So this is a switch capacitor circuit. We are using MOSFET as a switch and capacitor. So for this switch capacitor circuit, see the speed consideration. So we have to find out the T is equal to R into C. So speed is the time required for the output voltage to go from the 0 to maximum value of the input level whenever switch is turned on. So see, this Vin is equal to Vin 0, we apply the clock signal here. So clock will be go from a low value to the high value. So Vout will take the infinite time to become the input. So output is equal to input, it will take infinite time. So we will consider that the output is settled with some error band, and that is called as a change in voltage. So sampling period is given by the on resistance of transistor, on resistance of MOSFET, and value of this capacitor. So sampling time is equal to Ts is equal to R on, that is on resistance of transistor, and the capacitor Ch. So basically R on, that is the output resistance of the transistor, it is given by the equation, that is 1 upon mu n C ox W by L Vgs minus Vth. To increase the speed, to get the high speed of conversion, that output is equal to input, so we have to increase W by L ratio, and we have to decrease the Ch value. So to increase the speed, the T value, we will increase the W by L ratio and we will decrease the capacitor value. Now next point, that is a very important precision consideration. There are three mechanisms of transistor which will give the error in a switch capacitor circuit whenever transistor is turned off. So first error is the channel charge injection error. So basically we apply the input signal here, and clock signal is from high to low, we are applying here, and this is a Ch. So in a channel charge injection, when a transistor is turned off, so there are some charges present at the inversion layer, that is given by the equation QCH are the charges present in that inversion layer. Okay, so whenever transistor is turned on, channel is created, so at the silicon dioxide interface, so that inversion layer charges are given by the equation QCH is equal to WL Cox VDD minus Vin minus VTH. So this is the VGS voltage, that is a VDD minus Vin. So QCH is the charges present in a deflection present at the channel, and that is given by the equation QCH is equal to WL Cox VDD minus Vin minus VTH. So whenever this transistor is turned off, so these charges are trying to exist through this input side or at the output side. So whenever switch is off, this QCH will exist through source and drain terminal of transistor, and that is called as a channel charge injection. So channel charge injected at the left side is absorbed by the input signal, and right side charges are absorbed by the output. So it will give the error. So if you see this diagram, the input signal and output signal, so there is a difference in the signal. So this is a change in voltage. So this is the error created by channel charge injection. Due to the channel charge injections, error is created, and that is given by change in voltage is equal to, suppose half of the charges is injected at the output side, so it is given by WL Cox VDD minus Vin minus VTH divided by 2CH. So such type of error is we can call as a channel charge injection. So whatever the charges available in the channel is injected at the input side and output side when transistor is turned off, so it will affect on the output voltage. It will give the error, that is a delta V is the error voltage, and that is given by this equation. Delta V is equal to WL Cox VDD minus Vin VTH divided by 2CH. Next problem is a clock feed through. So between two terminal of transistor there is a capacitor. So see this is the capacitor between source, drain and gate. This is the capacitor between source and gate. So whenever there is a clock transition, this capacitor will couple at the input side and output side. So this coupling of this capacitor between two terminal of transistor will give the error in the output voltage, and that is given by the change in output voltage is given by the voltage of clock signal, width and overlap capacitor per unit width COV divided by width COV, that is the overlap capacitor plus CH. So this is a change in the output voltage. So this is a, we can say, a clock feed through. So clock signal is connected at the input and output side due to the capacitor between two terminal of transistor, that is capacitor between gate and drain and gate and source. So it will affect on the output voltage, and that is the error in the output voltage. Now next, that is a KT by C noise. So a transistor having output, we can represent a MOSFET as a resistor between source and drain. So resistor charging and capacitor will give rise to the total RMS noise voltage, that is a KT by. So RC charging will give rise to the total RMS noise voltage, that is a square root of KT by C. So on resistance of transistor will give the thermal noise. So we already discussed that there are two types of the noise, that is a thermal noise and flicker noise. So on resistance of the transistor having the thermal noise, resistor and capacitor charging will give this rise of the noise voltage, that is a square root of KT by C. So on resistance of switch will introduce a thermal noise at the output whenever switch is turned off. Now how to cancel the channel charge injection issue? So we are using a dummy switch M2. So these are the two transistor M1 and M2 is operated with the opposite clock signal. If you see this clock, so clock for M1 and clock for M2 are different. So whenever this transistor is turned on, this transistor will turn off, and whenever this M2 is turned on, transistor M1 will turn off. So channel charges which is present in a M1 will absorb by the M2, so we can reduce the channel charge injection issue. Now in this case we are applying input signal to transistor 1. So whenever this clock signal is high, transistor is turned on, so electrons are moving from source to drain. So inversion layer there are charges QCH. So whenever this transistor clock signal is low, transistor will turn off. So charges which are present in the inversion layer charges which is present in the channel will try to absorb at the V side, and it will absorb by the at the CS side. But at the same time the transistor M1 will turn on, M2 will turn on, and whatever the charges deposited by M1 is absorbed by transistor M2. So in this way, by using a dummy switch M2, we can cancel a channel charge injection. So for that we have to adjust the W by L ratio. Now see, these are the channels charges absorbed by M1, that is a charges Q1 is equal to W of transistor 1 WL1 Cox, a clock signal minus input minus VTH1 divided by 2. Suppose we are assuming that half of the charges is deposited on this CH. So these are the charges. So charges of M2 is width of M2, length Cox, a clock signal minus input minus VTH2. So if you compare this equation, so size of 2 transistor should be equal to 0.5 WL1, that is a width of second transistor should be equal to 1 by 2 width of 1, and length of transistor 1 and transistors 2 are equal. So in this way, whatever the charges deposited by this M1 will be absorbed by M2 if the width of M2 is equal to 1 by 2 width of M1 and length of L1 is equal to L2. So then and then only charges Q1 is equal to charges Q2. So in this way we can cancel the channel charge injection issue.